So last time we learned the definitions of row echelon form and reduced row echelon form. In this video, we will learn a step-by-step method of putting a matrix into row echelon form and reduced row echelon form. So to start off, let's look at this matrix 1, 2, 3, 15 and 0, 0, 1, 5. And I want to ask you, is this matrix in row echelon form? And is this matrix in reduced row echelon form? So let's start off with row echelon form. Remember, for a matrix to be in row echelon form, all rows of zeros have to be at the bottom of the matrix, which there's no rows of zeros here, so we passed that test. That the first non-zero entry in each row, that's non-zero, the whole row is not a bunch of zeros, the first non-zero entry is a 1, and that works. You see we have a 1 here and a 1 here. And we also have the rule that for each row that has a pivot, this leading coefficient here, that it's to the right of the leading coefficient of the row above it, which works in this case. So this matrix is in row echelon form. Now, is the matrix in reduced row echelon form? And the answer is no, it's not. And that's because one of the rules in reduced row echelon form is that it has to be in row echelon form. That passes. And the other rule is that wherever we have a pivot, there has to be nothing else but that 1. Everything else has to be a 0. And you can see that here's a column, and in this column I do not have a 0. So if we had a bigger matrix, remember, we'd have a bunch of zeros here above it and below it. And since I don't have a 0 above it, this is not in reduced row echelon form. However, I can put this into reduced row echelon form by just multiplying the last row by a -3 and adding it to the first row. So if we do that, what will we get? We'll get 1, 2, 0, 0, 0, 0, 1, 5. And now we have something in reduced row echelon form, because above the pivots we have 0. And I have a 0 here, but it really doesn't matter. It could be any number and this would still be in reduced row echelon form because there's no pivot right here. Okay, so what's the difference between a matrix and an augmented matrix? I've taken this same matrix here and I've put it right here, but I put a line in between the last column and the rest of the columns. So the difference is, once we put this line, what we're saying is there is a linear system that corresponds to this matrix. And the linear system for this particular matrix would be x1 plus 2x2 plus 3x3 is 15, and then x3 is 5. Each one of these entries in the row, they correspond to an unknown, which we label as x1, x2, x3. And then what's on the right of this line is the solution. So this is like saying it's equals, and then we put the solution here. And another way to express this augmented matrix is to say 1, 2, 3, 0, 0, 1 times x1, x2, x3 is 15, 5. So we can take any matrix we have, and if we just put a line separating the last column from the other columns, then that's like saying there's a linear system out there that corresponds to this matrix. So when we see an augmented matrix and we're asked to put it into row echelon form or reduced row echelon form, we do exactly what we've done before, like with this matrix without a line. We just ignore the line. And then when we put it into row echelon form or reduced row echelon form, then we think about linear systems. Okay, so when you put this in reduced row echelon form, just ignore the line the whole time, and then use the line when you're trying to find the solution to the system. Okay, so the next thing I want to talk about is what the reduced row echelon form of an augmented matrix would look like if a linear system is consistent and inconsistent. Okay, So first off, let's remind ourselves what consistent and inconsistent mean. So consistent means there's one solution or infinitely many solutions. And inconsistent means there's no solution. And an augmented matrix, remember, is a matrix that separates the last column from the rest of the matrix. Let's start with one solution. We've actually seen this already. Maybe it would be best to just make up an example for two equations with two unknowns. So x1 plus x2 is, let's say, 5, and x2 is 3. That one's easy. And then let's say x1 plus x2 is 5, 2x1 plus 2x2 is 10, and then the last one is going to be x1 plus x2 is 5, and x1 plus x2 is 6. Here I've just given you 3 different systems. This one has one solution, this one has infinitely many solutions, and this one has no solution. If I wanted to make the augmented matrix for each one of these, this is what I would get. And the question was, what would it look like? What would the reduced row echelon form look like if the linear system is consistent and inconsistent? Well, notice for the first one where we actually have a solution, x1 is going to be 2 because 2 plus 3 is 5. We're going to have one solution. If you put this into reduced row echelon form, all you have to do is get rid of this 1 here, so subtract it. You get 1, 0, 2, 0, 1, 3. So what's going to happen in this particular example, and in every example you have, is that you're going to have the same number of pivots as the number of unknowns. So here I have 2 unknowns, and here I have 2 pivots. And you can see I have this corresponds to x1 and this corresponds to x2, so that's how I get 2 and 3. That's what's going to happen when you have a consistent system with one solution. Now, what would happen if you have a consistent system with infinitely many solutions? Well, you're going to have less pivots than the number of unknowns. For example, this one, all I did was I took this line and I multiplied it by 2. So if you try to put this in reduced row echelon form, that means you want to get rid of this 2 here. What you're going to do is multiply this by a -2 and add it to this row, and you'll get 1, 1, 5, 0, 0, 0. And this is now in reduced row echelon form because, see, rows of zeros on the bottom, it's in row echelon form, and for all pivots, whatever is above them, you have zeros, and you can see you only have 1 pivot. So for this particular example, you have 1 pivot, but you have 2 unknowns. And you can see that this just says x1 plus x2 is 5. That would be an equivalent linear system, just getting rid of this equation here. And you have infinitely many solutions because 3 plus 2 is 5, but so is 4 plus 1, and 6 and a -1. So there's infinitely many solutions to this one. So what's going to happen is you have less pivots than unknowns, if that makes sense. So if you had n pivots, then the number of unknowns has to be bigger than n. So like n plus 1, or it could be n plus 5. You're going to have probably some rows of zeros involved. Now for something that has no solution, so this would be an inconsistent system. Notice that I have that 2 things added together give me 5, but at the same time when I add them I get 6. So why is this inconsistent? Well, let's put this in reduced row echelon form. All I have to do is subtract the first row from the bottom row. So I get 1, 1, 5, 0, 0, 1. When you have an inconsistent system, you're going to get something that's a false statement. Like if you did this just without using a matrix, you would see that if you subtracted this row, you would get that 0 is equal to 1, which is exactly what it's saying here, because you have 0 times x1 plus 0 times x2 is 1. This is a false statement. So whenever you have an inconsistent system, what's going to happen is you're going to have a row of zeros, but the last entry is going to be a non-zero number. So that's what's going to happen when you have an inconsistent system. Okay. So let me give you a nice way to put a matrix into reduced row echelon form. This is specifically for a linear system, so an augmented matrix, but remember you could always just delete that line. This works for any matrix, so it doesn't have to be an augmented matrix. It can be any matrix, okay? So the first thing you do is you find the first column from the left that's non-zero. I would definitely write this stuff down and then practice it when you're putting a matrix into reduced row echelon form. So you find the first column from the left that's non-zero. Let me give you an example. Okay, like this matrix here. The first column from the left, that's non-zero. Here we are, this is the first column, and is non-zero because not all of these are zero, okay? Now what you want to do is you want to exchange rows to get that non-zero number to the top of the column. So you want the first non-zero number you see, which is right here, you want to exchange the rows until you can get that one to the top of the column. So if instead I had something like this, for example, I want to move this first non-zero row that has this first non-zero entry right here. I would exchange these two so I can get this number to the top, okay? So that's the first thing you want to do. So you want the first entry in the first row and the first non-zero column to be something that's non-zero. So let me go back. Let's say that this is a 1 and a 2. I think this was a 0. Okay. Then you want to zero all entries below that column by elementary row operations. So for this particular example, you see that I have a 3 here. I want to get rid of it. And to get rid of it, I would need to multiply this row by a -3 and add it to this row here. So that's what I mean by zeroing all entries below that column by elementary row operations. So that's the first thing you're going to do after you make the top entry non-zero. Okay? After that, you want to ignore the top row and repeat. So we pretend like this row and this column here do not exist. So we go to the next one. So let me make a line here. So pretend like we did all of that. You look for the first non-zero entry in your column, which happens to be already right here. And then you get rid of all of the things below it that are not zero. So let's say I want to get rid of this -1. So I multiply this by 1/2, which means I have to multiply everything by 1/2, and I add it here. And that will get rid of this -1. And then I zero out, if there's other stuff, I'd also zero that out. Then I go to the next part, and I get rid of this 1 here by multiplying this by 1/2, and so on. Now this is a 4x4 matrix, so I've finished once I get here. But if it was a larger matrix, you would just continue this process. Okay. Oops. I'm not sure. I think that, I don't know what number that was there. Let's put a 3 or 2 here. So if you're working with an augmented matrix, at any point you get a row of zeros equal to a number that's non-zero, that means you have an inconsistent system. So here you could just stop and say, particularly if you're trying to find the solutions to the system, you just say this system is inconsistent. Now if we don't have an augmented matrix, if this is just a regular matrix, you don't have to worry about systems being inconsistent or not. The next thing you want to do is you want to make your pivots equal to 1. How you do that is you just divide every row by, let's say you had a pivot with a 2 in it, so you just divide that row by 1/2. You divide by 2, which is the same thing as multiplying by 1/2. And then that will make the pivot 1. So if you have a pivot with a -5 in it, then you need to divide by -5. Once you do that, you have a matrix, an augmented matrix in row echelon form. Now remember, the difference between reduced row echelon form and row echelon form is you have to zero out the things above the pivots. So to do that, you want to start at the bottom non-zero row and zero out the entries above each pivot. Then go to so you start at the bottom non-zero row, and then you go to the second non-zero row, and you repeat. So you zero out everything above the pivot, and so on. And then you'll have something in reduced row echelon form. Okay, let's do an example. Let's work through an example. Let's solve this system. Okay, let's solve this system. So we have 4 unknowns, x1, x2, x3, x4, and 3 equations. Let's put this in an augmented matrix. So take a minute and pause the video and write everything down. Okay, so I'm going to put it in an augmented matrix. Maybe you should do that first and just check to see if you get the same thing as I get. Here is my augmented matrix. Okay. Now let's start getting rid of anything below this 1. So this is, notice that I don't have a 0 here, so I don't need to exchange any rows to get my first entry to be a non-zero number. So now all I need to do is I need to get rid of the stuff below it. Okay, so I'm going to multiply row 1. So let's do it over here. In fact, I want to make this a little bit smaller so I have more room. There we go. What I'm going to do is I'm going to multiply row 1 by a -1, and I'm going to add it to row 2. That will get rid of this -1 here. Let's do that. I'm going to leave the other 2 rows alone. The only one I want to change is this one. And what I like to do is I like to write what I'm changing each one by above that row, just because sometimes people make mistakes. I make a lot of mistakes. So this is -1, -2, 3, -4, -1. So we get 0, -3, 1, -5, 5. Okay, I always double check too, because, oh, wait, sorry. I don't know why I did that. Let's undo that. I shouldn't have multiplied by a -1. I should have just added them. Okay, so let's do that. Let's put So if I add them, because I was thinking about getting rid of this -1, so 1 plus -1 makes a 0. So let's put 0 here. This becomes 1, 1, 3, 7. Okay, that should be correct. Okay, now we've gotten rid of this. We made this a 0. Now we need to get rid of this -2. So we multiply the first row by 2. Okay, so we're going to take 2, multiply it with row 1, and add it to row 3. What do we get? Well, we're going to leave the first 2 rows alone. And then I'm going to write above here 2, 4, -6, 8, and 2. So 0, 0, 1, 7, 3. All right, now we're in row echelon form. Notice that my pivots are all 1s. Here's a 1, here's a 1, here's a 1. Now something that could happen is I could have a 2 or some other number other than 1 here, and all I would need to do is divide that row by that number. Okay? Now let's put it in reduced row echelon form. So we start at the bottom where this 1 is, and we get rid of anything above it. So to get rid of this 1, I need to multiply it by a -1 and just add it. And to get rid of this, I need to multiply it by a 3. Now you can do these in one step. So you could say -R3 plus row 2. And you could also do +3 times row 3 to row 1. If you want to do it all in one matrix, you don't have so many different matrices you have to write out. So that means I'm going to leave the last row alone. Okay, let's take care of this one first. So I'm going to make this a -1, -7, -3. Add it to the top, the one right above it. So we get 0, 1, 0, -4, 4. Okay. Now let's erase this and let's take care of this one. So we multiply it by 3. So we get 3, 21, 9. And add it to the first row. So we get 1, 2, 0, 25, 10. Okay. Now, after we've zeroed out everything above this pivot, we go to the next pivot and we get rid of anything above that one. All right. So what I'm going to do is I am going to take row 2 and multiply it by a -2 and add it to row 1. I want to skip steps here. So 0, 1, 0, -4, 4, 0, 0, 1, 7, 3. Okay. I'm going to actually cross this out and put -2 times it right above it. So 0, -2, 0, 8, -8. And let's see what we get. We get 1, 0, 0. So 33. And then 2. All right. So now we have a matrix in reduced row echelon form, this augmented matrix, because we have 3 pivots. Everything below and above the pivots are 0. And it looks like we only have 3 pivots. And this original system, oops, This original system, you can see it had 4 unknowns. So we have less pivots than we do unknowns, which tells me that this is going to be an inconsistent system. So let me go down here. So we have, let me put this in green. We have 3 pivots, but 4 unknowns. Okay, and you can see and remember that if we had the right amount of pivots as the number of unknowns, we would just have a bunch of zeros everywhere. Here we don't have that. So we're going to have infinitely many solutions, and let's write down those solutions. So remember that this corresponds to x1, x2, x3, x4 is equal to, and this is our b. Okay, so we're going to get x1 plus x4 is 2, plus 33x4, sorry, is 2. Then we get x2 minus 4x4 is 4, just following this row. And this x1, x2, x3, so x3 plus 7x4 is equal to 3. Okay? We're going to solve for each one of the pivots. So let's write that here. Solve for pivots. If I do that, I get that x1 is 2 minus 33x4. x2 is 4 plus 4x4. And x3 is 3 minus 7x4. And this is our set of solutions. We have one free variable and 3 other variables that depend on that free variable. So what is this saying? Whatever we choose for x4, let's say we choose 0, we can find x1, x2, and x3. So for example, a solution would be if x4 is 0, then x1 is 2, x2 is 4, and x3 is 3. That's just plugging in 0 in for x4. You can choose something else for x4. Say if x4 is 1, you could plug in 1 here. You would get x1 is negative 31, x2 is 8, and x3 is, well, this would be 21, negative 18. So choosing anything you want for x4, you can't choose anything for x1, x2, and x3, but you can choose anything for x4, and then using that number you can find x1, x2, and x3.